Okay, welcome back. On the last video, we are seeing these solutions. We start our discussion about Euler angles. So we learn about the three angles of rotation, the phi, the theta, and the psi, and based on the direction in which this the axis in which we are applying um, this rotation based on the direction in which these axes are pointing, we were able to construct these matrices. And this way we were capable of find the total matrix of the Euler angles. So these angles, they are applied successively. So is a sequence of rotations, of transformations. And these transformations we can represent also in form of matrices, because now you know these elements is representing the orientation of the vector of some actuator, the position of the robot, and specifically these three first columns, and the last column is representing the position. And multiplying these three matrices, we got this total matrix, which is represent the final, not the final desired position, but it represents after these angles being applied successively. So in order to solve for these angles, we apply a inverse kinematic analysis, and for that we use a inverse transformation. And applying this inverse transformation and specifically above the a-axis with some phi angle, we were able to reduce this transformation equation, and we were left with this one. And this transformation equation is basically the solution. And in order to solve for each angle, we were assuming that our desired final position and orientation is this generic matrix of coordinate system, which is based on this reference frame and also in this moving frame. So we got these coordinates, and assuming that this matrix is our desired final position and orientation, we were able to construct equations. So for multiplying these matrices on the left side of the equation and on the right side of the equation, this transformation equation right here, we write this other equation with these matrices, and for each element on the left side of the equation on the matrix, we got a correspondent element on the right side of the equation on the matrix. And constructing these equations, we were able to solve for each angle applying a arctangent, applying the trigonometric relation, tangent is equal sine over cosine, and applying a arctangent having a pair of sine and cosine components, we are able to extract each of these angles of rotations, phi, theta, and psi. And on this video, what we were going to do is to solve a example. So is the example 2.23 from the third edition. So we are using the third edition, and the example that we will solve is the 2.23. Okay, so I will just write the statement and we will start to solve. Alright, so it says that the desired orientation, it's basically it has the same it's basically the same example that we were solving for the RPY angles, but now we are solving for the Euler angles. Okay, orientation of the hand of a now is a Cartesian Euler robot. Is given. So it was given this matrix with the respective values of the elements for orientation and position. And again, just like we have done for on this introduction, I was doing a quick review on how you can write a transformation, and just like we have done right here in this example, it fits perfectly for this first example, as the name of the interfactor, we name it H because of the hand of the robot, and also the two that we attach it, that we pick to attach it on the interfactor. It happened that we used the hand, so it fits perfectly for this first example. So again, is a transformation of the H frame in relation to the reference frame, and I can, let me just write this because it's very important to know. Again, is important right here in robotics context. I will keep repeating this because when the topic is robotics, it's very important to know how to write transformation equations, and these transformations are made of transformations. So right here, it's important to know how to write, how to read. So is a transformation of the frame H in relation to the frame or reference frame in right here is hand robot, just hand. And okay, and as you can see now is a Cartesian and Euler robot. So the respectively matrix and right here coordinate system was given, and as I was commenting, the generic matrix with the coordinate system that we adapt to solve for the solutions, it looks like pretty much the Cartesian one. So right, we have nx, ny, nz, n0, ox, oy, oz, n0, ax, ay, az, 0, and right here the components for each axis on the coordinate system for this Cartesian coordinate system. Okay, py, pz, 0, 1, sorry. And now the values of the coordinates. Minus 0.612, minus 0.354, 0.707, 0, and now 7, 2, 6, and 1. Okay, so again, it looks like pretty much right here, this we are naming a generic matrix of the coordinate system because we can also use these solutions for other coordinate systems, and also I propose to you to try to right here switch for the characteristical matrix of some respective coordinate system like the cylindrical one and the spherical one. So right here you substitute for the coordinate system of the respective coordinate system in which your robot is on it, and try to solve for each of these angles, and after compare with the results that we got for this right here. Okay, um, so this is the statement, and so we got this Cartesian or the robot. I think we don't need to draw any illustration. And he asked to us to find, so he asked to find the necessary Euler angles. Okay, and this will be easy because we already have solved for each of these angles, phi, theta, and psi. So like we were seeing for the RPY, maybe we can face a problem if we try to solve for a matrix that is given in its coordinates, that is given on a cylindrical or spherical coordinate system, because just like on the RPY, at least me, I face some problems. But as I'm saying, and I keep repeating, it must work. So if we got time, because we need to move on with the content, but if we got time, and if I could do a revision, I pretend to, I wanted to get back on the examples that I couldn't find all the solutions. I was able to find only 2 solutions, and maybe no, I find let's see, I find the alpha angle, and we use the alpha angle to try to solve at least the phi angle we were able to find, but the phi a angle, but phi o and phi n, I wasn't able to find the correct answer. And at least compare if the answer that I got on the book, it don't looks like pretty much like on the book. The results is diverging, but with more time I pretend to get back and try to find the solution or a explanation for this diverging of the results. But again, it must work for other coordinate system, and also if you try to solve for other coordinate system, the solutions, it must look like pretty much the same. So this is going to be very easy and very quickly because we already got the solutions. So the first one that we can apply is for the phi angle. So right here, and we also got a complementary solution. So let's see. The first solution is for phi angles, for the phi angle. So we got right here, let's see. is A10, so is the arctangent. We will extract the angle of this component, so AY and AX. Like I was saying, for each element on the left side of the equation, we got a corresponding element on the right side of the equation on the matrix. So AY, its corresponding element is this one, 0. minus 0.354. So let me just copy this. And its pair AX and AX, its correspondent on the right side is minus 0.612. So let me copy. And now we can go to the octave and evaluate this operation. And this will be equal to, okay, let's go to the octave. Let's clean the octave's memory, typing clear all. Now type CLC to clean the command window. Now we can type is phi dag is equal A10 to minus, let me see, 0.354, 0.354, and let me just do a adjustment right here. Let me switch for a point instead of this comma, and minus 0.612, minus 0.612, and right here I almost forgotten D, A10 to D, and minus 150 approximately. Okay, so is approximately minus 150 degrees. And right now we got a appendix A on the book, and it tells to us is a thing that we can check for this type of problem, something that we can consult. So if we got both components for sine and cosine negative, I think I can, because I don't got the book right now, but let me see right here, sine, and right here cosine. And now we have to managing the sinus for, so for sine right here is positive, and for cosine is positive also. Right here for sine is negative, but for cosine is positive. And right here both for sine and cosine is negative. And right here for sine is positive, but for cosine is negative. And I don't remember, I think it's the first quadrant, the second quadrant, the third quadrant, and the fourth, or is 1, 2, 3, and 4. I don't know. So if right here is 0, yeah, and right here 108, or I have to switch, I don't know, but I can correct this after when I got the book. So we can do minus 150 plus 180, which is equal 30 degrees, and that is the correct answer for the phi angle. In the complementary solution, we just have to switch the signals. So I think is easy. Let me just copy this line of code, and right here let me just switch the signals. So it's going to be positive because we are switching the signals. Actually, is the operation between the signals, and this is equal plus. Okay. And let's see what we got. 30 degrees. And now let's see if we do 30 degrees plus 180. Now we are right here on this quadrant. For now, I will erase this order because I don't know exactly the order, and on the next video I will pass the right order for you. And right here is 210, and this is the solution for the complementary one. Okay, we have solved it and find the solution for the phi angle. Now we can solve for, actually is already solved. We just need to apply the solution. Now for the theta angle. So for the theta angle, AX, again AX is corresponding to this value, AX, and now times the cosine of phi. So let's solve for cosine of phi. So is cosine of, I will just do for this solution right now. So cosine of phi is equal 0.866, and also sine of phi we're going to use, and sine of phi is equal 0.5. So let's continue with the solution. So now y, I forgot to multiply 0.866, and now ay again, this value, these elements, We can even put between parentheses to work with the sino and times 0.5. And this is the first pair, and this is the other pair, which is AZ. And AZ is equal 0.707, the second pair. So let me solve right here, which is equal 0.707. Okay. And now let's see on octave the value that we will get. Now is theta deg is equal 810 to the 0 point minus 0.707 and 0.707, and we got minus 45 degrees, minus 45 degrees. Nice, that is correct also. And for the complementary solution, like I said, we just need to do the operation between the sinus. The complementary solution is with the coordinates with the opposite sign. So if you try for the complementary solution, right here will be minus, right here is minus, so will be for the complementary solution, right here will be plus, the sign of plus, and right here minus. Okay, and now for psi, the last angle. Let's see, nx, so is this first element, nx times sine of theta, sine of phi, which is 0.866. No, it's sine of, 0.5 plus now ny, and ny is this element now cosine of phi, which is equal 0.866, and this is the first pair, and now the second one minus, let's see what is the sign on the element ox we have this minus sign. So doing the operation between the signs, we got this element as positive. And I will do in a correct way. So it's minus 0.773 times sine of phi, which is equal 0.5, and now plus OI, and OI is equal this value times cosine of phi. Okay. So for this first pair, we got 0.72 and for 724. And for the second pair, we got 0.454. Okay, so I can calculate warp psi. So again, let's use the octave. So now it's psi bag, which is equal 8 2d 0.724 and 0.554. Enter, and approximately 58 degrees. Let me see. Okay, we are not getting the correct result because again we have to pay attention, we have to be careful with the sign, because on the solution we got this minus nx, and on the value on the matrix we also got this minus on this first value. So actually right here is a positive sign. So let me correct this. So correcting right here is actually it was good that we have committed this error, because now you know that we have to pay attention on the sinus, and if you are trying to evaluate these solutions, and at the first time if you don't get the correct result, you just have to revise your solution and the values that you are using, and also the sinus. So right here is 891. Okay, so let's try again. And now it's correct. Approximately 63 degrees. And as you can see, this was very quick. And that's it. This was the example that I wanted to solve with you. Example 2.23. And right now, on the next video, articulated joints, and which is very short, a topic very short. And after fourth and inverse kinematic equations, more specifically about the position and orientation. And as we already has discussed it, we use the fourth and the inverse kinematic solution exactly to find to know where is located the joints of some robot, and where we wanted to locate the joints. So where is it and where we wanted to locate it, and is also a topic very short, and we are still using the third edition. And after this, we will start something very important in robotics, something that we will use very often, and is something that one of something that we will be using with most frequency, which is Denevit-Hardenberg. Sorry if I'm pronouncing that is wrong. Again, Denevit-Hardenberg. So we'll also discuss about Denevit-Hardenberg. Or on the next video, we can solve a example from the second edition and practice a bit more order angles. Okay, so for now is all. Is all that I wanted to pass to you on this video. It was very short, very easy to understand, and that's it. Hope you enjoyed, hope you like it, and thanks for watching. Thank you for following till here, and we are just beginning and just starting with this book, which is amazing. And see you in the next video. Thank you.